Okay, let's start. So good afternoon, everyone. Hope you enjoyed the your lab orals. Right? Not sure enjoy is the right words though, but okay, so last week we looked at continuous random variables, and we looked at a few very important ones. The first one was the uniform. Then we had the normal random variable. We had exponential. We looked at chi-square, log normal. But I think those are the most important ones we looked at. And one important aspect of it was to try to see when we make a change of variables, right? You have a certain random variable x, and you look at another random variable y, and what we did there is we tried to compute the PDF of y given the PDF of x. And this is what we did when we played with the normal random variable. This is what we played when we looked at chi-square and log normal. We started with normal random variable, and then we looked at a new function of this normal random variable to derive the PDF of chi-square and log normal. Okay, so let's see if this is still in your head. So this is an exam questions from a few years ago. Right, that essentially looks at computing in this integral, which is integral between minus infinity and 2.35 of 2 over pi exponential minus 2 mu u minus 2 squared du. Right, and there is a hint there. It's a probability course. There is a hint there, and they say make use of the standard normal table. Right? We looked at the standard normal table last week. Right? So just as a reminder, if you have a normal random variable, right, x is, for instance, normal distributed with mean mu and variance sigma square. The PDF of x is this. Right? When you look at this one and you look at this integral, you see there is some form of similarity there, right? So the first thing you can do is say, well, let's try to formulate this slightly differently and say I will keep my integral here, but now let's write this fraction here as something a bit more similar to what we have here. So I'm writing 1 over pi, and I'm writing 1 over 2 here. And I have a 2 there, so I multiply by 2, and I divide by 2. That's 2 pi 1/4. And I have the square root. Right, similarly, the argument of the exponential here, I can say this is u minus 2 square. And I can divide. I can say, well, 1 over 2 is 1 over 2 here, but I would like to have a 2 like this. So I can write 2, and then I can divide by 2. Right, du. What is this? Yeah. The variance is 1 over 2 or 1 over 4? The deviation is 1 over 2. That's right. Right, so this is essentially the PDF of u that is normal distributed with mean mu equal to 2 and a variance equal to 1/4. Right? So this is essentially the CDF of u evaluated at 2.35, or the the probability that that u is smaller or equal to 2.35 when n is given by this. Okay, so we can use a table, but then recall that actually when we look at the standard normal table, this is provided for standard normal random variable. So the first thing we need to do is to standardize this. So I can write u, remember what we did last week, as something like this, where z is normal, 0 mean, variance equal to 1. And so I have no standard deviation is 1/2 multiplied by z plus 2. And so I can say this is p of 1/2 z plus 2 smaller or equal to 2.35. This is the probability that z is smaller or equal to 0.7. Okay, so now we can look at the table. Right, so here, for instance, and you have 0.7 is here, and the CDF is there, right? So you have 0.758. Right? Okay? So that was well answered by, I think, most of the students. There was relatively easy questions, right? But this is really for you to make sure you understand this principle of going from non-zero mean and non-unit variance to something that actually standardized, right? This process of standardizing the random variable is something that is very important. Good. So, so we had those uniform, normal, exponential, chi-square, log normal. And I gave you a few examples last week, and I said, well, if you have a transmitter and you have a receiver in communication, where are you going to see all those different distributions? Where the receiver here, you have some noise. The noise is actually normal distributed. When are you going to see this and study this? This comes second year. Next term. You're going to look at this. The transmitter, the information, the way it's modeled, the optimal way of actually modeling this is using Gaussian inputs or normal inputs. So this is also using normal random variable. So the noise is normal. The input is often normal. Where you're going to see this comes year 3, year 4. And if you take information theory course as well in year 4, you're going to look at this quite a lot. Here you have this propagation channel here, right? So on top of this, this environment becomes random, is modeled using random variable. And this is where you have exponential random variable that play a role, chi-square, and the log normal. So all of them come into play. And so this is where you're going to see this 4th year comes as well, especially the wireless comes. Right, so this is not some random and useless distribution. Those are actually stuff that we use almost on a daily basis to design, for instance, communication systems. Good. So we finished the lecture last week with some notion of reliability. And we looked at the systems when we have components that are put in series and in parallel. What we're going to do today is essentially finish that section, which is not really difficult. It's just actually application of things we have done already, right? And then what we're going to do next, which is actually much more important, is actually started looking at multiple random variables, right? Which is a really key part of this module, and you can be sure you're going to have exam question on that part. Right, so we looked at those different circuits, series, parallel. This is something you're going to play with Bernie also in the class. A few things that we haven't talked about is a few definitions actually, or a few terminology that is used in this context of reliability. And the first one, when we talked about random variables in the context of reliability, one notion that comes quite often is a random variable t that we denote random time to failure. And this is simply a random variable, is a continuous random variable, and is typically considered as non-negative. But you can just view this as a random variable, but it has this funny name, random time to failure. And so if you look at the CDF of t, you can write ft of t, which is the probability that t is smaller or equal to t. Right? This is called failure time distribution. Right? Again, another funny name, but just actually is nothing else than the CDF. Right? So what that means is actually you're looking at maybe some components or some systems, and you're looking at what is the probability that essentially the time that actually this component or the system has functioned properly is smaller or equal to t. Then how can we define this? This is going to be an integral between 0 and t, between 0 because it's non-negative, of a certain quantity right here, f of t. And what is f of t is essentially the PDF of t that, again, in this context of reliability, is called failure time density. And so the failure time density can be written as the derivative of the failure time distribution, right? The derivative of its CDF, right? Good. If we look at the complementary of the CDF, we have this, which is 1 minus the CDF of t. So 1 minus the probability that t is smaller or equal to t, or in other words, the probability that t is larger than t. So the probability that actually a component functions properly at least t unit of time. And so this is called the reliability function. Right? It's nothing else than the complementary of the CDF. Okay, so if what this means, the probability that t still is larger than t, so essentially the probability that the component is still functioning at time t. Right, one more thing. If we defined some event, and I have an event A, for instance, that is the event that t is larger than t and smaller than t plus delta t, which delta is a very tiny interval, and B is the event that t is larger than t. So what we're looking at is you have a time t, you have the time 0 here, and you have delta t, right? And what we're looking at is what's the probability that we have A given B. So what's the probability that we have systems or components actually operating within this time interval, given that it has already worked properly t unit of time. So this is probability that B, the probability that A intersection B divided by probability of B. And so given that A is included into B, this is the probability of having A divided by probability of having B. So what is the probability of having B? Well, this is nothing else than what we had here. So that's the reliability function. Right? This is nothing else than P of t larger than t. And what do we have here? Well, we can approximate this. Let's imagine I have a certain distribution, right, of t, and I want to compute this quantity here, P of A. So that's a probability that actually is within this interval. So I have t and t plus delta t, right? And so what is this probability? Is essentially this area, right? So if delta t is very small, I can say this is this probability density function multiplied by delta t simply, right? Is essentially that value multiplied by the length of that tiny rectangular, right? So this is a relatively good approximation if delta t is sufficiently small. Right, so why do I do this? Because I'm writing this a little bit better. This quantity here is called z of t. This is called the hazard rate. So z of t is called hazard rate. And what it means is essentially it's a measure of how prone the system is to failure at time t. right? So you're essentially looking at this by doing this. You're looking at what's the probability that the system fails within this tiny time interval, given that it has operated correctly until time t, right? So you're looking at what's the probability actually it's going to really fail in the next delta t time instant. And so this is the hazard rate, and it's actually a measure of proneness to failure at time t. Right, so if this quantity is actually increasing with the time, essentially means that the system will be more prone to failure as time advances. Good, so this is another important notion that you find if you play with reliability, right? And so the last thing that we can define is essentially the integral of this quantity, which is called the cumulative hazard function. And what this says is this is essentially the integral, given time t, the integral of this hazard rate, and still between 0 and t, since t is non-negative, of the hazard rate. Good, so how can we write this a little bit differently? Well, I can plug this relationship into here, and so this is the integral between 0 and t of f the t u rt u du. And what's the relationship between the CDF and this, the PDF and this reliability function? Well, I can go back to here and say, well, f of t here, my CDF, right, is nothing else than 1 minus the reliability function, right? So this is the derivative with respect to t of this quantity. So this is 1 minus the reliability function. And so this is minus the derivative with respect to t of this reliability function. Okay, so what do we have here? What you see is that we have something that looks like we have a relationship between ft and rt, so that ft is the derivative of rt, right? So we have here ft is the derivative of rt. This ratio resembles something of logarithmic. So this is the minus logarithmic of this function t, evaluated between 0 and t, right? The derivative of this would be 1 over rt multiplied by this derivative. Okay, so with this, we can plug this into this relationship, and what do we get is minus ln of rt evaluated at t plus ln of rt evaluated at 0. And so what is this reliability function evaluated at 0? This is the probability that t is larger than 0. This is equal to 1 because t is non-negative, right? So this quantity becomes 0. And so we have a relationship that says this cumulative hazard function is minus ln the reliability function, or in other words, the reliability function is exponential minus the cumulative hazard function. Okay, so these are not really new concepts, is essentially new terminology that is used in this context of reliability. I personally do not use this often because I don't look at those problems of reliability, but this is something that you can see. It's something that actually is quite popular in different areas, not only in electrical engineering. So just to get some insight, let me give you an example of what that means and try to relate to something that we have seen in the past lectures. So let's imagine that I have a hazard rate that is given by lambda. And lambda is a constant, right? So that means actually the proneness to failure is a constant, whatever the time t, right? So once we have this, what can we do? What we can calculate first, we can calculate this cumulative hazard function is the integral of the hazard rate. So I have integral between 0 and t of zt of u du, the integral between 0 and t of lambda, and the u, that's lambda t. Once we have this, then we can calculate the reliability function, right? So that's reliability function is E minus this cumulative hazard function, so E minus lambda t. And now we have the PDF, right? Or this failure time density is essentially the derivative minus the derivative of the reliability function minus the derivative of this reliability function. And what we get is lambda E minus lambda t. Okay? So what that means here is that this is just a different way of looking at a random variable t that is exponentially distributed with parameter lambda. This is the PDF of an exponential distribution, right, of an exponential random variable. And so what that means is if t is exponentially distributed, its proneness to failure is a constant, right? So this is nothing else. This is reminiscent. This is reminiscent of the memoryless property that we looked at last week, right? Where remember, in the memoryless property, we said if t is exponentially distributed, the probability that t is larger than a plus b, given that t is larger than a, this is equal to the probability that t is larger than b, right? This quantity is not a function of a anymore, right? And essentially what we're saying here, we're saying the same thing but differently using this hazard rate. And we're saying the proneness to failure is not a function of the time, it's constant. Essentially it's the same as the probability that the component works properly a plus b unit of time, given that it has worked a unit of time, is just a function of this quantity b. Okay? So that's the memoryless property we saw last week. That's this hazard rate. The two actually essentially connected. They mean the same thing, but they express differently. Right, so this is one type of distribution. You have a hazard rate, and I explained last week. If t is, for instance, the lifetime of human beings, well, it's very unlikely you can model lifetime of human beings using this random variable t that is exponentially distributed, because indeed our proneness to failure is not constant, whatever our age, right? As you get older, you're more prone to failure, I would say, right? So in this case is not something that would be used for human beings, but it's something that can be used for components. You're looking at semiconductor fabrication, maybe your component, they will not wear over time, they will not get old, and this is the way it can be modeled using probability theory. So you can have other types of hazard rates. So let me give you some example here. If you can see the figure, right? You have here some example of hazard rate that are flat, right? So this is the exponential random variable that we saw is flat. But you can have some of them actually decreasing, something like this over time. Or I have a hazard rate that is increasing, or I can have this kind of bathtub behavior here, which is decreasing, flat, and then increasing, right? So if your hazard rate is decreasing like this, essentially that you're more prone to failure in your early age. So this is probably typically what's happening in your manufacturing process if you have very cheap components and badly done. Many of them will just fail very early on, right? If you're more prone to failure as time increases, this is maybe something you can have with human beings, even though it's not totally accurate, because, for instance, in some countries you have the mortality rate is quite high when you're young or when you're baby. So in that case, you may have a proneness to failure or hazard rate that is higher at young age, right? Then it's more or less flat, and then you have something that increases. So maybe this bathtub behavior here of this hazard rate maybe is more representative of human population, at least lifetime of human population. Right, so this is used in various fields. Right, you can use this in health economics. You can use this in different fields of economics. You can use this in electrical engineering if you analyze reliability of components is used in many different areas. Now, there are different distributions that can be used to model this. I will not go into all those details. But one of them is called Weibull distribution. It's a little bit complicated one. You see it's a bit nasty. But essentially it's a function of two parameters. And the usefulness of this is because you have two parameters, you can play with, you have more degrees of freedom. And so you can have hazard rates that are actually decreasing. You can have hazard rates that are increasing. You have lots of flexibility. And so this is something that you will play a bit in the classes. So this is an example here what's happening with this Weibull distribution. Well, you have this beta parameter which enables you to have either a decreasing hazard rate as a function of the time if beta is smaller than 1, and if beta is larger than 1, you have actually a hazard rate that is increasing. Right? That's essentially the flexibility of this Weibull distribution. Okay, so with this, we're almost done. The last thing I want to introduce is, aside this cumulative hazard function and hazard rate, is a quantity that is called the expectation of t, the expectation of this random variable t, which is mean time to failure, right? So essentially it's nothing else than the theoretical mean or the expectation of this random variable t. And so this has a certain property, which is this quantity is nothing else than integral between 0 and infinity of t multiplied by its PDF, right? And there is a common way of writing this that says that actually this is the integral between 0 and infinity of this reliability function. And this works well if you can show that the mean time to failure is strictly bounded. It's never equal to infinity, right? So this is an expression that is sometimes used, and it works well if this is bounded. You have the demonstration in the notes if you're interested in. It is not something that we're going to really look at a lot. It's just an expectation of t, essentially. Okay, so nothing really fundamentally new, but the terminology can be a little bit confusing. And this is sometimes used in some discipline. That's why actually I'm introducing this. Okay, so with this, I think we're done with the first, I would say maybe first part of this module, which was dealing with a single random variables, right? Now we're going to start looking at case where we have multiple random variables, and this is something that's becoming maybe more interesting because this is a problem that we have to face in practice very often. And so if I have a communication system, right, and I have a transmitter again, and I have a receiver. You have seen this quite many times now. You have noise. I model this using a random variable. I have here some data that I transmit. I model this using random variable as well. Let's say x. And now what I have at the receiver, I have x plus n. So if you remember what we said at in first lecture, we say in statistics, we try to say something about x, because x has been corrupted by some form of noise or some form of uncertainty, right? Now in communication, you have x is modeled as a random variable. And why is it a random variable? Simply because you don't know the information that will be transmitted, right? You have 0 and 1, they come randomly. If everything is deterministic, you don't convey any information. You need some form of randomness in the message in order to convey information. So x is a random variable, and n is a random variable, right? So now you have the sum of two random variables, right? So this is a problem, for instance, where you have two random variables, and so the question is how are you going to model this? And rather than looking at each random variable independently, we need to look at them jointly, and this is why we define the notion of jointly distributed random variables. Right, so we looked at if you have a random variable x, we looked at the CDF of x, right? And we looked at the PDF and the PMF, right? If it's discrete or if it's continuous. Now we have multiple random variables, so I may have two of them. Let's say I have random variable x and y. I have two of them. And similarly, I can define also a CDF, which we call joint cumulative distribution function, and is written as something like this: f of x comma y evaluated at, for instance, a and b. And so what that means is the probability here, this is the probability that x is smaller or equal to x. So now this is the probability that x is smaller or equal to a and y is smaller or equal to b. And so this here means really and. Right? You're looking at this event occurring and this event occurring. Right, so this is something that you can see when you have x and y are discrete. They can be also continuous. And so the first thing we're going to look at is first a case where x and y are discrete random variable. So let's imagine I have two random variables, x and y. And an example of this is x means I'm throwing a die. And y is I'm tossing a coin, right? So if I'm doing both of them, I can have a sample space that now is not only given by 1, 2, 3, 4, 5, 6, or head or tail here, but I have a combination of those two, right? So I can have, for instance, the event 1 and head, 2 and head, all the way to 6 and head. Or I can have 1 and tail, 2 tail, all the way to 6 and tail. Right? So that would be my sample space here, because I have two random variables. They each have their own domain, and so the total sample space now is given by this. Right, so we had this probability mass function when we had a single random variable. Now we can define a probability mass function when we have multiple random variables. So how do we call this? We call this joint CDF. Now we can call this joint PMF. Right, so I have a joint probability mass function. And what is this joint probability mass function? Is essentially this is essentially the probability that x is equal to x and y is equal to y. Okay, and so if I want to look at a certain probability of an event, and this is obviously, this has to be a valid PMF, right? So this has to be a valid PMF. That means that this has to be positive, right, for all x and all y. And if you sum over all realization of x and all realization of y of this joint probability mass function, you should get 1, right, in the same way as what we had for single random variables, right? That would essentially mean that the probability of the universal event occurring is equal to 1. Again. Good. So if you want to have, if you're looking at the probability of having a certain event occurring, so I have a certain A here, and I'm wondering what actually this will occur. This is essentially a sum over all possible x, all possible y, such that the couple, the pair xy belongs to a certain domain A of this joint probability mass function, right? So I can give you an example right away, right? So if I have two random variables, and I will use this relationship here. So if I have two random variables x and y, so I have x and I have y, and x can take different values, 1, 2, 3, 5, 6, 7. And I'm given the joint probability mass function. So the joint probability mass function is given by this, for instance. Right, so what that means actually the probability of having x equal to 1 and y equal to 5 is equal to 0.2. Right, that's the essentially the joint probability mass function. that is given for all values of x and y. And so if I'm interested in a certain event A that is, for instance, 1, 5, 2, 6 here, and 3, 7, I'm looking at essentially those diagonal entries here, right? This will be the probability of having this pair of random variable actually belonging to this set A will be given by the probability of having x equal to 1, y equal to 5, plus probability of having x equal to 2, y equal to 6, plus probability of having x equal to 3 and y equal to 7. Right? So essentially I'm doing this. I'm summing all my PMF over this especially specific domain. Right? So I can write this differently. This is f of xy evaluated at 1, 5 plus f of xy evaluated to 6 plus f of xy evaluated 3, 7. Right, so this is the sum of those three entries, the 0.2 plus 0.1 plus 0.1, that's 0.4. Okay, that shouldn't be a major problem. Good, so with this we have a joint probability mass function. So how can we get from here to the PMF of x and the PMF of y? So in the context of multiple random variable, this is what we used to call previously as PMF. Here we're going to call it marginal PMF. Right? Simply it means that is to distinguish from the joint PMF. This is the marginal PMF of x. This is the marginal PMF of y. So it's to just distinguish from this one that is a joint probability mass function. Now from the joint probability mass function, I'm looking at the probability of x equal to x and probability of y equal to y. Right? So how can we do that? Well, we can take the joint probability mass function and we can sum. So I can take the marginal of x. The marginal PMF of x will be the sum of this joint PMF over the other random variables, over y. The marginal of y is the sum of this joint probability mass function, but over the other random variable, which is x here. Right? So in the example we had earlier on here, what does that mean? That means that if I'm looking at the margin of y, I'm looking at the joint probability mass function, and I'm summing over all realization of x. So I can do this here. I'm taking at this joint probability mass function when y is equal to 5, and I'm summing over x. So the sum of all those rows will give me 0.3, 0.4, and 0.3. That's going to be the marginal of y. The marginal of x is obtained by summing this joint probability mass function over the rows now, over y. So I will have 0.5, 0.3, and 0.2. Okay? So from here you can indeed write in that example that I have x is 1, 2, 3, and the marginal of x is given by here is 0.5, 0.3, and 0.2, right? And the marginal of y, that can take values 5, 6, 7, is given by what we have here, 0.3, 0.4, 0.3. Right, so those two are actually marginal PMF. They're still PMF. They have to satisfy those properties. So fx of x has to be larger and positive. Fy of y has to be positive, right? That's the first condition. Second one, the sum over x of this PMF has to be equal to 1. The sum over y of this marginal has to be equal to 1. And that's what you see. The sum is equal to 1. The sum is equal to 1, right? So those are indeed valid marginals, valid marginal probability mass functions. Okay, so with this, I think we have the main tools to play with discrete random variable. let's look at what's happening if you have no continuous random variable. So if we have continuous random variable, we don't have a sum anymore. We can still define this joint CDF that still holds. But now, rather than having a joint probability mass function, we're going to have a joint probability density function. Right? So now I can introduce a joint probability density function, which is given by the following. If I'm looking at a certain domain A, and so if we had with single random variable, we had the following. This is the integral over A of the PDF of x, right? Now, if I'm looking at a domain A, but when I have multiple random variable, I'm going to have the probability that actually this pair x, y is belong to a certain domain A will be now a double integral over this domain A of a certain quantity here, and this quantity is called this joint probability density function. So what that means is I have a certain domain, let's say for x and y. For instance, I'm interested between x going from A to B and y going from C to D, and so I have this domain here. And I'm integrating a joint probability density function over this rectangular domain. That would give me the probability that indeed this event occurs. Right, so this is, again, so how can we write this, right? A, in this case, is a rectangular domain. So if for this example here, I'm going to have, if this is A, the probability of x, y, given being included in A, will be the integral between A and B, integral between C and D of this joint CDF, joint PDF, dy dx. Okay? So what we had before with this PDF here still carries on here. This is a joint PDF. This was our, let's say, normal PDF or marginal PDF. This had to be valid. This one still has to be valid. That means actually this quantity here, this has to be a valid PDF. So the joint probability density function has to be larger or equal to 0, right, for all x and all y. And second one is similar to what we had here, where the sum of that joint PMF over all x and y was equal to 1. Now we have actually the integral of xy dx dy over the whole domain has to be equal to 1. Okay? So far, all what we have seen with single random variables essentially carries on to multiple random variables. It makes the calculation a bit more complicated because now we're playing with essentially multiple integrals. And so if you have that, if you have actually so how can we define the CDF now? So the CDF or the joint CDF that we had here, the joint CDF, right? The joint CDF will still be fxy a b, right? So that's the integral between minus infinity and a minus infinity and b of this joint PDF dx dy. And now what I can do, I can obtain the PDF, the joint PDF, from the derivative of this joint CDF, but now I'm taking a second order derivative, a partial derivative with respect to x and with respect to y, right? And by doing so, assuming that actually the derivative exists, you can actually obtain the joint PDF. So that was similar to what we had here when we were taking one order derivative of the CDF of one random variable. Now we have two parameters, two variables, so we take the partial derivative of this joint CDF with respect to x and with respect to y. Okay, so let's see an example again to see how this works. So let's look at this following joint PDF. I have a joint PDF that is given by 6 over 5 x plus y squared, and this is when x is between 0 and 1 and y between 0 and 1, and otherwise I have 0. Right? So this is a joint PDF. Is that a valid PDF? That's the question we try to see first, right? So to be valid, this has to be positive for all x and all y. This is correct, right? Second, the integral between minus infinity and plus infinity of this joint joint PDF should be equal to 1, right? So in this case here, what do you get? Integral between 0 and 1, integral between 0 and 1 of 6 over 5 x plus y squared dx dy, and you can do this at home and you get 1. Okay? This is not very complicated. Here you have a domain that actually is just a rectangular, so you can actually easily change the order of integration if you like, but you should get 1. Okay, so with this, we know how to play with joint CDF, joint PDF. How do we get, similar to what we had here, how do we get the marginal of x and y? So that's, again, an interesting and important question. So if I have the joint PDF of x and y, how do I get the marginal of x and how do I get the marginal of y? So this is the marginal, not PMF, but PDF of x. This is the marginal PDF of y. Okay? So for discrete, what we did was to compute a sum over the other random variable, right? For continuous, what are we going to do? We replace the sum by an integral, essentially. And so the marginal of x will be given by this joint probability density function where I integrate with respect to the other random variable. And the marginal of y is the integral between minus infinity and plus infinity of this joint PDF when I integrate with respect to x, because I'm looking at y. Okay? So what that means is actually if you have a certain joint probability density function, and you can see this as actually a three-dimensional shape, you have x and y, and then your joint PDF is some kind of hill, if you like, right? What you're looking at when you look at the marginal is there, you're looking at the integration in one dimensions and then the other dimensions, essentially. Good. So one important thing is that you note that if you have this joint PDF, you can compute the marginal of x and you can compute the marginal of y, right? If you have the marginal of x and the marginal of y, you cannot necessarily compute the joint PDF, right? So the joint PDF actually carries more information than its marginal, and in some case you can reconstruct the joint PDF from its marginal. We're going to see some of those, some case later on today, but in general is not the case. Okay, so let's look at two scenarios. So one relatively easy and one a bit more complicated. So let's have an example where the domain that I had here, for instance, is rectangular, right? So I have a rectangular domain. And I have a joint probability density function that is given by essentially the example I was just giving just earlier on, where indeed we have that the domain for x and y is square, right? So how can I compute the marginal of x here? Well, I can say this is the integral between minus infinity and plus infinity of the joint probability, the joint PDF, and I integrate with respect to y. Right? So in this case, it will be the integral between 0 and 1, 6 over 5 x plus y squared dy. Okay, so this is 6 over 5 x y squared over 3, 0, 1, 6 over 5 x plus 1/3. Okay, so this is my this is my marginal of x, and for x given between 0 and 1, and otherwise it is 0, right? Because outside of x between 0 and 1, essentially the joint PDF is 0, right? So I'm integrating the joint PDF over y, and now I'm obtaining the marginal of x. For x has to be contained within that domain here. Right, same, you can do the marginal of y, integral between minus infinity and plus infinity of this joint PDF, integral between 0 and 1, 6 over 5x plus y squared dx this time. And so that's 6 over 5 x squared over 2 plus y squared x between 0 and 1 at 6 over 5. 1 over 2 plus y squared, right? And so this gives you the PDF of the marginal PDF of y, right, equal to this when y is between 0 and 1, and otherwise is equal to 0. Okay? So here this is relatively easy because essentially we have this domain is square. So when I take an integral here, I integrate between over y here is just between those two boundaries. Those two boundaries are not a function of x, right? Now, one scenario that may be a bit more complicated is when I have domains that are non-rectangular. So now I have a non-rectangular domain. And before going to this, if you have to compute a certain probability, right, probability that x is smaller or equal to 0.5, for instance, what can you do? You just compute this integral of fx of x dx, where f of x is given by this quantity, right? So you actually can use this exactly in the same way as what we did with single random variables. Right, so what if we have a non-rectangular domain? So let's have an example here. I have this joint PDF that is given by this 24xy when x is between 0 and 1, y is between 0 and 1, but I have an additional constraint here that says x plus y has to be smaller than 1, and otherwise it's 0. Okay, so here we have a domain that is not square. Right? We have something that is like this. I have x, I have y, I have 1, 1, 0, and 0. And so this would be my square domain, but additionally I have this constraint there. Right? So x has to be smaller than 1 minus y, or y has to be smaller than 1 minus x. So we have here this extra constraint here that says that the domain now we're looking at is essentially this one. Okay, so how can we show first whether this is a valid joint probability density function? Right, again, fxy has to be positive for all x, all y. This is okay. Second one is the integral between minus infinity and plus infinity of this joint PDF has to be equal to 1. Right? So how can we compute this here? We have a domain that is non-square. So I can integrate, for instance, with respect to fixed x. X goes between 0 and 1. I have this joint domain here, this joint PDF, which is 24xy. And now I need to integrate over y. So if I fix x here, if I fix x, y can vary between 0 here and 1 minus x. So it can vary here on this segment between 0 and 1 minus x. Right? So integrate between 0 and 1 minus x. Okay, is that clear? Right? You can view it the other way around. You can say, well, I integrate with respect to x first, and then with respect to y. So y will go from 0 to 1. If I fix y here, for instance, x will vary between this point here and this point there. So between 0 and 1 minus y. So I have 24xy between 0 and 1 minus y. It's okay? Right, so this is something that actually sometimes some students have some troubles. Right, when domain is non-square, you have to be really careful about essentially the boundaries that you use for the integrals. Good, so with this, if you do this, you can do this at home, you get 1. Okay, so what can we do? What can we do next? Well, if I have this, if I want to look at, for instance, a certain domain A, which is given by all pairs of xy, such that they're indeed between 0 and 1, y is between 0 and 1, but additionally I have a constraint x plus y is smaller than 0.5, then essentially I'm here. I'm looking at maybe this domain here. This is 0.5, 0.5. I'm looking at this probability of having x and y being included in that domain. So the probability of having xy here within A, what will it be? It will be the integral, and I can reuse what we have here, but rather than having 1, in the integral between 0 and 0.5, 0 and 0.5 minus x, 24xy dy dx. Right? Or if you want to integrate with respect to the other random variable first, is 0.5 minus y, 24xy dx dy. Okay? And now if we want to compute the marginal of x, right, so I have the marginal of x. That's the integral between minus infinity and plus infinity of this joint PDF with respect to y. What do I have now? Careful, if I integrate with respect to y here, y is such that y has to be smaller than 1 minus x, right? And y has to be positive, so I'm integrating between 0 and what? What would be the boundary? If I'm looking at the margin of x when I have this domain here, this joint PDF, what should be the values here? This is 1 minus x, right? Because we have that the domain is x plus y has to be smaller than y, so y is 1 minus x. Okay, so when you compute the marginal, same thing. Be very careful about the domain, right? If the domain is square, it's easy, right? If I didn't have this relationship here, if I ignore this one, well, it would probably not be a valid PDF. But then I could just ignore the 1 minus x and just write 1. But because I have this additional constraint, I have to be really careful here that actually this boundary is itself a function of x. Okay, so be careful. Every year in the exams, I have mistakes about those boundaries, right? Good. So let's have a break here for, say, 10 minutes or so, and then we're going to start looking at independent random variables. Should we resume? So let's look now at the notion of independent random variables. So you remember what we did with when we had two events that were independent. I was saying that the conditional probability of A and B, with A and B events, if this is equal to probability of having A, then A and B are independent. And this had for the consequence that the probability of the intersection between A and B was P of A multiplied by P of B. Right, you remember this, right? So what if now we have X and Y are random variables? How can we define independence between two random variables? Well, there are essentially two ways of doing it, and they're actually equivalent. The first one is based on the CDF, and so we can say that the probability of X being smaller than X and Y being smaller than Y, this is equal to the products of their respective probabilities. Right, so that means actually the joint CDF evaluated at xy is essentially the product of the CDF of x evaluated at x and the CDF of y evaluated at y. And this has to hold for all x and all y. Okay, it has to hold for all x and all y. So if this works for some x, but not for some other, for some x and y, but not for some others, it will not be independent. It has to hold for all. Okay, so this is based on CDF. You can define this also based on the marginal, based on the probability density function or the probability mass function. So you could say the so xy are independent random variable. So the joint PDF of xy is equal to the product of their marginal for all x and all y, or in terms of discrete random variable, the probability of having x and y is essentially the product of their probability. Right? So let's say this is for continuous, this is for discrete. Okay, so but here again, it has to hold for all x and all y. So this is why I was saying earlier on, if you remember this, I said that if you know the joint PDF, for instance, you can compute the marginal of x and the marginal of y, but you cannot necessarily reconstruct the joint PDF if you know only the marginal, right? So you can do it, you can go the other way around if they're independent. If they're independent and you know the marginal of x and the marginal of y, then you can indeed construct the joint PDF simply because the joint PDF is equal to the product of the marginal, right? So in that case, it's fine. You don't lose any information between the joint PDF and its marginal, but if they are not independent, then the joint PDF contains more information than just the marginal, okay? Good, so so we had this example earlier on in the module, right? We had this here. We had this example here, right? So you can look at that and say, well, are x and y here independent or not? Well, to see whether they're independent, you would have to compute, see whether actually this quantity is equal to the product of this with that, right? And you can see relatively quickly that actually indeed the product of this with that is not equal to that, right? So in this case here, you note that the joint PDF of xy is not equal to the products of their marginal. And so those x and y here are actually dependent. They're not independent, they're dependent. Okay? So you have to be careful. In general, you have to look at this for all x and all y. Same if it's a discrete random variable, it has to hold for all x and all y, that the product of marginal has to be equal to the joint PMF. If it doesn't work, if it works for some but not for some others, there will be a dependent. Good, so what if we have more than 2? So if we have more than 2 random variables, well, we can extend all what we did to some more complicated scenario. And so, for instance, if I have n random variable, x1 all the way to xn, I can define a joint CDF as well. I can say my joint CDF will be f of x1, x2 all the way to xn, evaluated at x1 all the way to xn, right? And this is the probability that x1 is smaller than small x1, x2 smaller than x2, all the way to xn smaller than xn. And you can define the joint PDF by saying that x1, x2 all the way to xn, assuming the derivative exists, you can take the nth order derivative of this joint CDF with respect to x1 all the way to xn. Okay, so you can do this as well for n random variables. And if they're independent, random variable, then this joint CDF evaluated at x1 all the way to xn will be equal to the product of the CDF of x1 evaluated at x1 multiplied by the product of the CDF xn evaluated at xn, right? And this has to hold for all x1, x2 all the way to xn. Or equivalently, you can say the joint PDF of x1, x2 all the way to xn is equal to the product of the marginal of x1 all the way to the marginal of xn. And again, for all x1 to xn. Okay, so that holds as well. Okay, so in this module, we'll not play with more than 2, but you can use it, right? It's something that you may use in other modules. We will often play with 2 random variables. In some case, at the end of the modules, we can play with some more. But essentially, what we have seen so far actually holds for n random variables. Good. So with this, we have the joint PDF. We have the marginal. And let's look at another notion that we have seen we have seen in the past, which was the conditional probability. So when we looked at conditional probability, and we had 2 events, and we were saying probability of A given B was the probability of A intersection B divided by probability of B. Well, now we can look at the similar notions, but when we have random variables. So we can define the notion of conditional probability mass function and conditional probability density function. So here what it means is that you have a certain realization of y, for instance, and you're looking at what's the conditional probability, the conditional probability density function of x given y. Right? So you try to also examine what's the influence of y, for instance, on the PDF of x. Right? So here I'm writing the conditional probability density function, for instance, of y given x, right? And I'm writing this again with this vertical bar. Y given x, so for y evaluated at a certain small y, for x evaluated at a certain small x. And this is equal to, a bit similar to what we had here, we're going to have a joint probability density function of xy divided by the marginal of x. And this holds whenever this is positive. Okay, so this is the definition of conditional probability density function, and it holds also for discrete random variable, right? So in that case, this is actually the conditional probability mass function is given by the joint probability mass function divided by the marginal probability mass function of x. And this quantity is still a valid PDF or PMF, right? So that means that this has to be positive, right? And the integral of this quantity, with respect to what? With respect to y, because now x is given. I have a given value of x. So I'm integrating with respect to y. Between 0, minus infinity, and plus infinity should be equal to 1, right? So it's still same as PDF or PMF. If you have a PMF, you sum over all realization of y, and this has to be equal to 1. Right? So is that true? Well, we can see this. We can say, well, let's replace this by this relationship here. So I have xy divided by fx of x, and I integrate over y. I can take 1 over fx of x outside, so this is 1 over the probability density function, the marginal of x, integral between minus infinity and plus infinity of the joint PDF of xy with respect to y. And what is this? This is the marginal of x. Right, so it's equal to 1 indeed. Okay, so it's indeed a valid definition. Right, and so if you have this marginal CDF or PDF and you want to compute, for instance, the probability of having y is smaller than a certain value, given that x is equal to something, well, that's the integral of minus infinity to y of this conditional probability density function of y given x over all y. And if x and y are independent, so you can use this exactly as we did earlier on when you define the CDF. If x and y are independent, what is happening? Well, you know that we can write this. This is this. If they're independent, this is equal to the product of the marginal of x and the marginal of y divided by this. And so this cancel each other and you get fy of y. And this has to hold for all x and all y. Right? So you see indeed that if they're independent, the conditional PDF of y given x is actually the same as the marginal of y. Right? So this is a little bit reminiscent of what we had earlier on where we say P of A given B is equal to P of A. Okay? But now that holds not for probability but also for probability density function or for probability mass function of random variables. And this has to hold for all x and all y because this relationship here holds for all x and all y. Okay, good. So just an example of this. Right, we had this earlier on. We had this function here. We had 6 over 5 x plus y squared, and we had a square domain. And 0 otherwise. And what we compute earlier on is the margin of y. So we'll write it here again, 6 over y squared plus 3 over 5, between 0 and 1 and 0 otherwise, right? You remember this? We just did it here, essentially. So how can we compute the conditional PDF here if I'm looking at, for instance, the conditional PDF of x given y, for y equal to a certain value, so y is equal to 0.3, for instance, so I have y equal to 0.3. So what am I doing? I'm saying I'm looking at the joint PDF of xy, x at, well, for y is 0.3 divided by fy of the margin of y evaluated at 0.3. And so what you get is 6 over 5 x plus 0.3 squared. here given by this, divided by the marginal of y, evaluated at 0.3, that's 6 over 5, 0.3 squared plus 3 over 5. Right, so this is actually the marginal, the conditional PDF of x given y, when y is given by these values, and this is for all x between 0 and 1, essentially. And otherwise, essentially 0. Okay, so this is the notion of conditional probability. So we looked at conditional PDF and conditional PMF. So we looked at the joint CDF, the joint PDF, the joint PMF. Then you have the conditionals ones. And now we can look at something else. We can look at expectation. Right, so you remember what we did with when you have a single random variable x, and we were looking at expectation of x. Right, that was the integral between minus infinity and plus infinity of x fx of x dx. Right, have a certain distribution. I'm looking at where this distribution lies around, right? That's essentially my theoretical mean. I can define something similar, but not for multiple random variables. Right, so before going into this, if I have no a function of x, right? If I have a function of a certain random variable x, this is still a random variable, right? So I can define expectation of y. Right? And I can compute this. Now, there are two ways we can compute this. Either I first calculate the PDF of y, and then calculate expectation of y as integral between minus infinity and plus infinity of y fy of y dy. This is one way. Right? Or you could say, I'm saying that expectation of g of x is the integral between minus infinity of and plus infinity of g of x multiplied by the PDF of x. Right? So those are two different ways of doing it. So when we looked at, for instance, the log normal random variable or the chi-square random variable, what we did, we tried to find the PDF of that random variable. So from there, you can actually, after compute its theoretical mean or its expectation, right? But what you could do as well is to compute an expectation of a certain function directly by computing this without having to compute the PDF of y, the PDF of g of x. So sometimes it's much easier. If you're only interested in the expectation, it's easier to compute this directly rather than first going through the PDF of y and then compute the expectation, right? So those are two different methods that you can use. Now, if you have multiple random variables, and now I'm interested in looking at this, what is the expectation of a function of two random variables x and y? And those two may be dependent, independent. Well, it's a bit something similar to this. What I can rely on is the joint PDF of x and y. I don't need necessarily to compute the PDF of this new random variable, which I can call z, for instance, even though we will look at this later on in this course, how we could do this. But maybe one simpler way would be to compute this directly. So what I can say is that this is going to be a sum over x, a sum over y, of g of xy multiplied by the probability mass function, the joint probability mass function. And this is if it's discrete. Right? And if it's continuous is then the integral between minus infinity and plus infinity of this function multiplied by now the joint probability of x, y. Right? So this is actually a very useful property, and we will look at a few examples now, but essentially the intuition is the same as what we did earlier on. The PDF, when you compute an expectation, is always a form of weighted average. So actually, this is your weight, and you're looking at that function, and you weight by actually that probability density function, right, or joint probability density function in this case. Right. So let's take a few simple cases. Let's imagine that g of xy is simply equal to x. Right? So now I'm looking at expectation of g of xy is expectation of x. Right? So expectation of x is something we know. We should get the integral of x multiplied by the PDF of x. Right? So let's see if this works. We get, and I'm using this definition here. Right? So I have now a double integral between minus infinity and plus infinity of g of xy, which is now x multiplied by the joint probability density function of xy. Okay? And so I integrate with respect to y first, so I can do that. X integral minus infinity plus infinity fy xy dy dx. And what is this? This is the marginal of x. So this is indeed the definition as we know of the expectation of x. Okay? What if now this function gxy is simply x minus mu xy, right? Where mu x is expectation of x. Well, so here I can do the same thing. I can say now expectation of g of xy is expectation of x minus mu x squared, which is the integral between minus infinity plus infinity of x minus mu x squared multiplied by the joint PDF dy dx. Right? And I can do the same thing as before. This is again going to be an integral of x minus mu x squared of an integral of the joint probability density function of xy. I integrate with y first, so this is again margin of x. And this is something you should know. This is the variance of x. Right? Okay, so indeed, if this function g of xy now suddenly does not become a function of y, as in those two cases, we boil down to what we had earlier on in the course. Right? We get the expectation of a single random variable, we get the variance of a single random variable. What if we have g of xy is x plus y? Right, so now expectation of g of xy is expectation of x plus y. This is integral between minus infinity and plus infinity of x plus y multiplied by the joint PDF of xy. Right, and now I can break this into two integrals. X, and I have 2x multiplied by fx of x dx, dy dx, plus integral, double integral y joint probability density function of xy dy dx. Right, now you must be familiar with what we've done, right? What is this? This is expectation of x. And what is this? This is expectation of y. Is that clear? Right? Again, you can take x outside, and then you have an integral of a joint PDF. This is the marginal, right? So you get x multiplied by the marginal of x, and you integrate over x. This is expectation of x, exactly as what we did here. Okay, so if we have expectation of x plus y, this is expectation of x plus expectation of y. Right? I'm not making any further assumptions there, right? I'm not saying they are independent. I'm just saying we have two random variables, x and y, and you're looking at the expectation of x plus y. This is the sum of the expectation. What if we have this? X multiplied by y. So expectation of xy is xy multiplied by the joint PDF of xy So this is equal to expectation of x multiplied by the expectation of y. Make sense? Yes? No. That's wrong. Right? Cannot do that. Right? So don't make that mistake. I can see this many times. This is not the same thing. We'll see again when this can happen. We'll look at this next lecture, but the expectation of the product of x and y is not equal to the product of the expectations, right? The sum, expectation of the sum is equal to the sum of the expectation, but not the products. Good. Right, so let's look at simple example. Right, I have what we had earlier on. So we have, again, I have x and I have y. X can take 1, 2, 3. Y can take 5, 6, 7. And I have this joint probability mass function that is 0.2, 0.1, 0, 0.2, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, and then we can compute the marginal of y. We had 0.3, 0.4, 0.3, marginal of x, 0.5, 0.3, and 0.2. So what if now we want to have g of xy is equal to x plus y, and we want to calculate expectation of x plus y, right? So you can do two things. Either you can say this is expectation of x plus expectation of y, right? And you can compute this. This is a sum over all x of x multiplied by fx of x, and this is sum over all y of y multiplied by the marginal of y. So you're actually using this and using that, right? Or you can say, well, this is expectation of x plus y. This is a sum over all x, a sum over all y of x plus y multiplied by the joint probability mass function. Right? You can do that as well. Right? Essentially, it's exactly what we did here. Right? I'm writing here expectation of x plus y, actually this. Now I have discrete random variables, so rather than having an integral, I have here a sum. That's what I can do. But I can say that actually this is also the same as e of x plus e of y, so I could compute it just by computing e of x and e of y. Right, so those are two different ways you can do this at home. You get obviously the same answer. So in this case, you would use that. You would use those values here in the middle of the table. If you do that, you would use the marginal here, those values here on the side. Okay? I'm sure you can all do this by now. Moving on to next notion, we looked at conditional PMF, and we looked at expectation. So now we can combine those two notions into conditional expectation. Right? So it's an expectation, but it's conditional on something. Right? So because it's conditional on something, you expect that actually this expectation will change. Right? And how do we write this? We say expectation of x given y. Right? So what is this quantity? This quantity is the conditional expectation, is a random variable, is still a random variable, function of y. So it's a random variable and is a function of y. So I can say this is like a g of y. Right? So let me define it. How do you define this quantity? So let's look at y is equal to a certain value y, and I'm looking at defining this function g of y is expectation of x given that y is equal to this specific value y. So how can we define this? Well, similar to what we had with this conditional expectation and with this conditional probability, you see that you have a conditional, conditions here. So what you expect is you're going to get a conditional probability or conditional probability density function or conditional probability mass function. Right? So if it's an expectation, so what that means is a weighted sum. So I sum over all x, multiply by what? Multiply by the weights. No, the weights are given by the conditional PMF. So I'm looking at the probability summing over all I, and I'm looking at P of x equal to xi given that y is equal to y. Right? I'm looking at taking here the conditional probability mass function, essentially. So this is the discrete case. And what about the continuous? You can imagine what you're going to get. Right? In the continuous case, you take an integral now between minus infinity and plus infinity. You have an expectation over x, so this is why you have x coming up. And then you have a condition over y, so you're actually using the probability, the conditional probability density function of x given y, and you integrate here over all x for y equal to this quantity. Right? So what you see here, and this is very important, is that this quantity here, right, if I evaluate as for a certain value y, this is a function of y. Right? It's evaluated for a specific value of y. So if I have y is equal to 0, 1, 2, and so on, I can have ex of y that will be here, e of x given that y is equal to 0, e of x that y is equal to 1, e of x that y is equal to 2. Right? So you can really view this as a function of y. Right? This is different from e of x. E of x is just a number. Right? You compute the expectation of random variable x, what you get is a number. Is the mean of that distribution. You have x, you have the distribution of x, and you get e of x is just a number. Here, this is not a number, it's a function of y. So it's a function of y is still a random variable. Right? Okay, so this is very, very important. So we're going to play with this today for the last, the remaining 10 minutes, and then we're going to continue this next week. So what's happening if now we have x and y are independent? So imagine that x and y are independent. X and y are independent, right? So I'm taking a certain y for all values of y. I'm looking at expectation of x given that y is given to that. And so I'm taking the definition here. I have integral between minus infinity and plus infinity. I'm assuming it's continuous of x multiplied by f of x given y dx. Now, because they're independent, what do we have? Because of the independence, we know that fx of y is equal to f of x, right? Right? If x and y are independent, fy given x, the condition of y given x is equal to actually the PDF, the marginal of y, right? So here, if x and y independent, the margin of x, the conditional PDF of x given y is equal to the marginal of x. And so we have indeed that this is the integral between 0 and infinity of x multiplied by the marginal of x, and this is expectation of x. Okay? So if they're independent, the conditional probability of x given y is equal to the marginal of x, right? Y does not influence the marginal of x, or the y does not influence essentially the conditional probability density function. Is actually this one is equal to its marginal, and if they're independent, the expectation of x given y is equal to the expectation of x, so y does not really influence the expectation. Right, so what if we have the following now? So keep in mind that what I was saying is that expectation of x given y, this is essentially a function of y. Right, so for every value of y here, you can compute this conditional expectation, so it's a function of y. Right? So if I'm writing expectation of x given y, and I'm taking another expectation here, right? What does that mean? That means that I'm having here a function. This is a function of my random variable y, right? And I'm taking here an expectation of a function of y. So this is an expectation with respect to y. Right, so I'm writing y here specifically so that you know to which random variable we take the expectation. Right, so let's try to see what is this equal to. So this is a function of y, so this is actually an expectation with respect to y, so I'm writing integral between minus infinity and plus infinity of g of y multiplied by the marginal of y. Right, I can do that. This is simply the definition of what we had earlier on is g of y, right, is equal to that. Right, but now my g of y, what is this g of y? G of y is equal to expectation of y given y. So g evaluated as small y is expectation of x for y given by small y. And this is, again, I have my definitions here earlier on, right? I'm using this, right? This is an integral between minus infinity and plus infinity of x multiplied by the conditional probability density function of x given y dx. Right, so I can take this and plug this into here. You all follow? Right? So this is a, I'm writing a here, is equal to integral between minus infinity and plus infinity x multiplied by the conditional probability density function of x given y multiplied by the probability of y dx dy. Okay, so what do we do with that? Well, what do we do with that? We go back to the definition of conditional PDF, and you see that if you take this term and you bring it to the other side, what you have is fxy xy is equal to the CDF of x, the conditional PDF of x given y multiplied by the marginal of y. And so this is here the joint probability density function of x and y. And this is, again, equal to integral between minus infinity and plus infinity of x minus infinity plus infinity of this joint PDF, and say dy dx. This is the marginal of x. And so this is x fx of x dx. This is expectation of x. Right, so if I do expectation of, conditional expectation of x given y, what I get is expectation of x. Right, this part's getting a bit more complicated, right? So here we start using a lot of different notions, and you have to become familiar with this. Yes?
So if x given y is a random variable, right? It's a random variable.
Which one? This one.
Given y.
Yes. This is a random variable, is a function of y.
Right. And it has its own, obviously as a random variable, it has its own distribution function.
That's right. So this is a function of y. This is a function of y. That means actually it's a function of y. But when you compute this expectation, you see, because you compute expectation with respect to y, this is like the function you're looking at, and then you multiply by the PDF or the marginal of y. Right?
Because it's just a function of y.
because it's a function of y. So what we're doing is essentially this. We say it's just a function of y, so this is the integral of this. Right? This is exactly what we're doing here. And we're doing this here. We start this, we say the expectation with respect to y of a function of y is just this. But now this function of y has a specific structure. And that specific structure, we write it here, that is actually written itself as an integral. And that's why we can plug this into this first relationship. Right? So what you do here, essentially what you do is that rather than writing expectation of x, you say, well, I will break this expectation into two expectations. I will first take an expectation of x with respect to y, and then I will take an expectation with respect to y. Right? So I take first a conditional expectation of x given y, and then I actually average over y.
So if we look at this in terms of the probability mass function, the discrete case, the joint one, would that basically be equivalent of looking at the mean of every individual row and then taking the mean of those means?
The means of those means.
Like what because you know how like you have x here and then you have the different values of y here in this table thingy.
Yeah.
Then when you take the mean of each row, isn't that essentially equivalent to saying the probability of x given y for that specific y?
So if you look at from the table, you can say here, you're going to have a sum of a function with respect to this. So you're going to use one of those PDF, or one of those PMF, and that function here will be itself, well, a conditional expectation. So that will be written as a sum. Let me take the expression so that you understand better. A sum here. So you're going to have to you're going to have to first compute this quantity. So you're going to sum over x, but you have to compute this quantity first, which will be a ratio between some of those elements that you have there in the middle of the table and some of the marginal. I'm not sure you can explain this that easily. Yeah. But the idea is the following. You're looking at expectation of a random variable, and rather than computing it directly by saying I will compute it using the joint probability distribution function, the density function, or the joint probability mass function, I'm breaking this into two steps. I'm saying that actually I first condition on y, I fix y, and I'm looking at this conditional expectation of x given y, and then I'm taking expectation over y. Right? So this is why actually this double expectation ends up being the same as the original expectation. Yeah. Okay? So this part I know is getting a bit more complicated because you have a lot of expectation and function coming into play. You're going to have to be a bit familiar with this. I will stop here today, and you can see next Friday we're going to go one step further. And so I want to stop here so that you can get a bit more familiar with that concept. But otherwise, I see you next Friday. Okay? Thank you.